Okay, on to homework 5. If we're looking at homework set 5, we address some things out of a few chapters here. For for number 13, we were looking at why it's so important to study patterns in elementary school math and how does that connect to algebra. Okay, basically, algebra is the study of generalized patterns, which most of you saw that. You wrote that as part of your example. When you are creating equations and modeling with data and modeling with equations, you are essentially trying to show a pattern in a more simplified way. And many of you discuss that much, much differently. But yes, learning patterns in elementary school builds conceptually to algebra because it's the same kind of thinking that's being used when we're using the strategies and ideas set forth that they learn in algebra. Number 2 asks, what misconceptions do students often have regarding the equal sign, and how do activities involving true and false and open sentences help clear these up? Well, first of all, hopefully you read that many students believe the equal sign to mean that they are to do something, they are to find some answer. And I see this actually when I grade and I score a lot of homework, because there will be many of you who write math sentences and you will tell me you need to solve the equation, when what you're really trying to do is just evaluate a statement or evaluate an expression. Okay, so equations and expressions are not the same thing. You do need to know the difference if you're going to use that terminology in your classroom. If you're at an age level where that's what you use. So an equation, we should be thinking of it, students should be thinking of it as a balance. And if they're not doing that, then they're not viewing it properly in terms of the symbolism. That has a lot to do with the fact that when we give students problems, we usually give them problems that say 4 plus 3 equals, or 6 times 5 equals. The blank is always on the right side of the equal sign. So they come to be conditioned to believe that when they see an equal sign, that means produce an answer. You've often heard me talk about being good at math does not mean you become a calculator where you hit enter and the number gets spit out. That's what differentiates us from machines, the ability to think higher. So what would help? True and false and open sentences can help clear that up. Of course, true and false forces them to think about the balance between the statement. If you give them a problem or a setup that says 4 plus 3 equals 9, true or false, they do have to consider and think about that. Of course, there are other types of true and false statements. You can also have open equations where they have to think about balancing the equation themselves. 4 plus box equals 10. We have to figure out what goes in there, and the idea of reiterating that equal sign is a balance. Your textbook showed some fabulous examples of balancing activities that you could use. That would be the straight of a good number talk, which I know you're currently looking at what number talks are on the discussion this past week. So definitely an important concept to understand. A lot of this also comes from the fact that we teach so many non-contextual problems. Non-contextual, of course, just means there's no context. It's not a story problem. You just have 7 plus 2 and you have to find the answer. They don't have to take that time to relate the context into symbols. They just always have the symbols without thinking about what they mean. So it's a little bit of the issue there that comes from their struggles with the equal sign. Okay, chapter 17, this question 3 is where we had the most of the struggle that we worked with here. It asks you to describe in your own words what a ratio is. Okay, now if you looked it up from the book, there's not really anything wrong with that, but hopefully after you looked at that, you do have some better concept of what a ratio actually is. And if you use the definition in the book, it says a ratio is a number that relates two quantities or measures within a given situation in a multiplicative relationship. Okay, Reasoning with ratios involves paying attention to two quantities that co-vary. Okay, now how does that relate to the idea that a fraction is a ratio and ratios can compare two parts of the same whole? Now, when it comes to talking about fractions, ratios and fractions are very, very closely related. They are a comparison of numbers, and it's not necessarily through multiplication, more like through division or parts of, but they're really more of overlapping concepts. Okay, now when we think about examples like what your book showed, you can have a description of an amount that can be both a fraction and a ratio, or it can be either or. The example your book gave was three statements. The ratio of cats to dogs is 3/5. The ratio of cats to pets is 3/8, and Mario walked 3/8 of a mile. For example, the first one, it's a ratio when we compare cats to dogs, but it's not a fraction. Okay. Why is that true? Because cats and dogs are not, they're parts of the set of pets. Cats are not part of the set of dogs. Okay. So when we talk about fractions, that is a part whole relationship. And fractions cannot be part, they are part whole. Although sometimes a ratio that compares part looks like a fraction because it's used with that same bar as the symbol. Okay, ratios can compare two parts of the same whole. Several of you tried to explain this, but you used a part whole comparison. If you think about a bag of marbles, which has 20 marbles in it, and let's say 6 are red and 14 are blue. If we think about a fraction here, which is part whole, we could have 6/20, which is the 6 red out of all 20, or we could have 14/20, which is the set of all blue out of the entire set of 20. That's a fraction, a part out of a whole. However, if we're going to compare part to part, that would be a 6/14 comparison, or if we simplified it, a 3/7, okay, because it has a common factor of 2 comparison. Whole part to whole is definitely going to be a fraction and a ratio, whereas part to part, that's going to be a ratio but not a fraction. Okay, hopefully that makes sense a little bit. So number 4, ask you to use a ratio table. Now, there's a very specific reason why this statement is in here. Calculations based on equations, cross multiplication is not allowed. Can't do percentages. You can't cross multiply. We are dealing with these questions from the mind of an elementary student. They're not going to set up equations and cross multiply. You're not going to either. It's not even a good idea to teach them to set up those equations and cross multiply if they don't understand why they're doing that or why that equation actually works. Now, I do have an example here of a ratio table that I thought was really good. Okay, this is a student who has created a ratio table that first breaks down every 30 minutes to 1.5 miles, 60 minutes, 3 miles. So it's using the basic ratio that we're given. Every 30 minutes we walk or we travel, we get another 1.5 miles. Okay, now here's what I like and what made this so good and so much better than just stopping here. Okay, although yes, this is a ratio table and most any of us could produce this. If you went then and tried to answer the questions that I posed to this table alone would not help you to answer those questions. The 1.5 hours and the 2 miles are not on there. So we had to do some sort of thinking. You couldn't do calculations, that was specifically outlawed. You had to do some sort of reasoning and thinking in order to reason that. And that's what makes this such a great example, is that this person went further and said, with the above information using the ratio of 1:3, I can further break down the distance every 10 minutes. Basically here, or no necessarily if we think of 1:3, it's more like 3 parts to 3 parts. We're taking 1/3 of each one of these, okay? For every 10 minutes, we're going 1/2 mile. That is the realization that has happened here. And as this person broke that down and broke that mileage traveled down in 1/3 for each one of these, then we're able to see that relationship just a little bit closer. We see that when we travel 2 miles, it clearly took 40 minutes. We see that when we have gone 70 minutes, which is an hour and a half, we have gone 3.5 miles. So as long as you had some sort of way of breaking it down, of saying, I know that 30 minutes and a mile and a half can all be broken into thirds, which would give us 10 minutes, 10 minutes, 10 minutes, and half a mile, half a mile, half a mile. And I get a more smaller of a unit comparison here, so I can be more specific and don't have such big gaps between the values that I'm calculating. Okay, so of course that person was able to answer those questions perfectly. And then we look at question number 5. It asks you to describe in your own words the first 3 Van Hyle levels of geometric thought, 0, 1, and 2, and how would activities aimed at 0, 1, and 2 differ. Now, lots of you did not do that in your own words. You pulled some specific things from the book, which isn't totally unreasonable because many of you may not have heard of these levels before and may not know what we were talking about. So you may have not had a chance yet to process that. Okay, so level 0 is, of course, visualization. If we're looking at level 0, basically you have a student who considers shapes based on what they look like. Okay, a triangle is a triangle because it's a triangle. It's not about its sides. It's not about its angles. A lot of students who are working at this level, if you were to turn that triangle sideways and present it to them, they would have trouble being able to classify if it's still a triangle. These are students who also fail to recognize that if you take a square, for instance, and it's oriented on one of its sides, and you were to rotate it to where that it's oriented on one of its angles, in other words, making it look more like a diamond shape, even though we recognize that it's still a square. More like a diamond, not exactly like a rhombus, because we know those sides are slanted. Nonetheless, if you were to take that square and rotate it up to where we have 2 opposite vertices, vertical and horizontal, the student would have trouble identifying that as a square because it no longer looks like a square. So level 0, some very basic understanding. If you move into level 1, that's analysis, okay, where students move from considering classes of shapes to focusing on the properties of the shapes. So we're talking about what makes a triangle a triangle. Of course, it has 3 vertices, it has 3 sides, some of 180 degrees. Okay, so we're looking at some of those attributes of each individual shape class. Level 2, of course, is informal deduction. Students move from considering properties to exploring relationships between properties of geometric objects. So we sort of are deducing here. If I tell you that, for example, all squares have 4 90-degree angles, and you see a strange object that has 4 90-degree angles, is it a square? Okay, here's where we're using our if and then statements. Mostly at the elementary level, we're going to be working with students who are either at 0 and 1 most of the time. That's not an always case, but in elementary, most of our students are going to be 0 or 1. And how would activities start to transition them into higher levels of learning or higher levels? This question doesn't even ask you to address 3 and 4, which is deduction and rigor. Okay, again, because that's usually at an upper level in which students are going to be working on that. So what influence do activities have? If you look through your book, there were specific activities given to move students between levels. Okay, of course, to go from 0 and 1, we would want to focus on the properties rather than identification. So any activity that would do that we would be taking them from just looking at simple identification to thinking about what makes that figure. That would be more appropriate from a 0 going into a 1. If we're going into 2, here we would have to start to challenge students to explore and test examples. Okay, give them a shape and ask them, does argue that this meets a certain classification. Lots of different answers that could have come from this question. It's kind of hard to narrow down exactly what you might choose. But most of you gave really excellent descriptions of this, and this was one of the higher scoring homework sets. If I were going to focus on something, I would definitely look at that ratio table and in question 3 and think about what that really means to be a ratio and how part to whole and part to part look different.